Hello SGD, Sacred Geometry Decoded. This will be a redo of part 9 of this series, Understanding the Great Pyramid and the Ancient Sciences. I just want to add some clarification to a certain point, and also I'll put just a little bit more info in there. So this is a redo to that series. So it's all about the geometry and some of these connections. But so we over here have a free Giza pyramids and the Great Pyramid there, or the Pyramid of Khufu or Cheops. This was a pyramidion, a capstone found next to the Red Pyramid, but it's not a capstone of the Red Pyramid because the angles are all wrong. I would suggest it's a metrological device, just like the Salamis stone or the metrological relief found in ancient sites, where essentially there would be a stone with inscribed marks, or the stone itself would provide systems of measurement so that people could calibrate their rulers and their measuring rods. But the Great Pyramid, 440 Egyptian royal cubits at the base, 280 Egyptian royal cubits high. Those are idealized measures, and we'll go into more detail because the base length has slight variations in it, depending on what side. But at 440 wide at the base and 280 high, that's a 7 high to 11 wide ratio. The Pyramid of Meidum has that same 7 to 11 ratio, and it's also scaled to the Great Pyramid at an 8 to 5 ratio, which is, just built into the geometry. All these pyramids have wonderful connections in regards to their proportions to each other, and but anyway, the capstone or pyramidion, it was a few years ago now, was refurbished, altered, but when it was originally placed together, the base length of it is 3 Egyptian royal cubits, or pi over 2 meters by 1 meter high. That also gives it a 7 to 11 ratio. And if you think about the triangle, so we're at 7, 11, the isosceles triangle, or 14 to 11, the right angle triangles that make that up. Now 7 to 11, we see that, so if the half base is 1, then the height is 1.272727, and the slope is 1.61859, giving us an angle of 51.84277 degrees. Now it's very interesting because, so for instance here we see on the other side, if we, therefore if the height is 4, the half base is almost equal to pi, almost. If the half base is 1, then the height is almost, that's why it's a squiggly line rather than a normal equal sign, the square root of phi, or the golden ratio, and the slope is the golden ratio, or very close to it. To have a perfect Kepler triangle, which would give you the golden ratio, or phi, the angle would be 51.8272924 rather than 51.84. Now, I'll deal with that sort of later on in the series, because each side of a base length of a pyramid has a slight variation, which means there's a slight variation in the angles, and these very close approximates of pi and phi come to essentially perfection above what's measurable in that sense. Also, as I mentioned, the delium problem, squaring the circle, and this is where I make a clarification. So compass and straight edge geometry, or the old-fashioned like Euclidean geometry. So what you can do with a compass and a straight edge, there are 4 problems: doubling the cube, angle trisection, squaring a circle, constructing a regular heptagon, or a 7-sided polygon / 7-sided star. Now with compass and straight edge, it's on paper mathematically impossible. You can get, again, absolute perfection. It's impossible because of the transcendental nature of the way things work. But there's, on paper impossible, and then so even you can construct a square on paper perfectly. When you draw the lines, you're not going to construct it perfectly. So there's mathematical perfection theoretical on paper, But then there's, any sort of construction, whether it's, geometry on a piece of paper or whether it's actual building itself, there are the real world issues of perfection come in. Or it gets even even a square is impossible to construct perfectly because the thickness of your ink will vary and all those features come in. But squaring the circle. Squaring the circle, construct a square whose area equals that of a given circle. So the area of that square would have to be the same area of a circle. Now, can you do that with compass and straight edge? No, you cannot. You can get a very, very close approximate above what you could actually, again, construct in real life. But squaring the circle is also, so you might have heard the expression, how to square a circle, basically means an impossible problem. Jung mentions it as well. But now, there's another way to think about it, and that's squaring a circle, is to construct a circle whose circumference is equal to the, I should have said, perimeter of the square. Now, there I have the Great Pyramid profile 7 to 11, and it's found elsewhere as well. It's because of the nature of the seched, that's one of the angles that were able, that even with ancient Egyptian geometry forms that are verified to create those angles. But 7 to 11, the pi and phi. So again, where there is matter, there is geometry. And in regards to squaring a circle, to have a circumference equal to the perimeter of the square. Or otherwise, the perimeter of the circle is equal to the perimeter of the square. So just overlay the Great Pyramid 7 to 11. And you have those proportions. Very close approximate to squaring the circle in that sense, but it's not the pure form of squaring the circle. But since the base of the pyramid is 11, therefore the square has a perimeter of 44. Doesn't matter what the units are for the moment. And since the height of the pyramid is 7, therefore the diameter of the circle is 14. Multiply by 14 by pi to get the circumference of the circle. So working off the ideal 7 to 11 proportions, or 440 cubits base by 280 high, you see how close it gets. Very, very close. However, the pyramid is not a perfect square at the base. It's actually like, this is a trapezoid, and this is like the pyramid is much less trapezoidal than this. Just as an illustration, the south side is the longest and the north side is the shortest. There is a taper in the Great Pyramid, and this is from the J.H. Cole survey, which also shows our Petrie survey. Now they have varying feet, and you can see, so the north side 755.4, 755.4, both by Petrie and Cole, but the south side, the longest is 756.072 or 756.084. So therefore the pyramid is not a perfect square at the base, and throughout this series I've looked at that, and if you apply this imperfection to the ratios and to the geometries, the very close approximates become perfect. Perfect to 10 decimal points, sort of above what's realistically being able to measure even with top-notch equipment. So pyramid is slightly different on each side. So there you see the in feet or meters, and I've also shown it here in ERC, or Egyptian Royal Cubits. So the shorter side is 439.75 Egyptian Royal Cubits. The longer side is 440.12. Now the ideal measure would be 440 at each base, but it is not, again, because there's about a 20 centimeter difference between the north and the south side. And so we get an average of 439.96, based on the Egyptian. So again, that's 440. We're talking millimeters, and just by the nature of the stone that's left, they're able to use imprints on the corner to get very accurate. But we're still, splitting hairs at that point, and the nature of stone over hundreds or thousands of years to lose fractions of a millimeter as well. But so back to squaring getting the perimeter of a square equal to the circumference of the circle based on the 7, 11, 44 and 43.98. The height of a pyramid, 280 Egyptian royal cubits based on the proportions. So what you would require to have a perfectly equal perimeter of a square, or the base, and the circumference of that circle would be 439.82975. So again, right in that point, again, well within acceptable margins of error, and because now it's essentially impossible to get to the micron measurements, and even in the past, just by the nature of things, contraction, expansion with heat and cold, a couple of grains of sand get worn off the stone, someone kicks it or drops a rock on it, that can change, it changes it by fractions of a millimeter, and so those issues are in there. But just to be more specific and just to clarify, when I'm talking about squaring a circle in regards to the pyramid, it's creating a circumference and a perimeter of the square, not the pure form of creating equal areas. But the issues in doing this are essentially the same. It's the transcendental nature of pi. But so that's again, it's right in that sort of sweet spot. And this 7 to 11 has been, whether it's Stonehenge, now 14 high with 11 half base, therefore 11 and 3, so 14, 11 or 3. Oh geez, I wish I should have included those pics, but I'll try to find the links, because Space Creator Band channel has looked at, for instance, the Dendera Zodiac that also has this geometry in it, and also the copper plate by the famed alchemist John Dee. He looked at that and found the same thing as well. But this is you'll find it in geometry across time, architecture across time. The Louvre pyramid, that famous glass pyramid by I.M. Pei, that's its proportion to this same sort of thing as well, and that was no mistake. It was meant to be that way. It's something that these architects, both ancient and modern, are doing, but it's in one of those sort of creepy areas. And so, but anyway, this same geometry also has another awesome aspect, and that is in regards to astronomy. So if the square defines the Earth, then the moon is defined by that separation. If you think about radius, so that and this image are exactly saying the same thing. I just prefer this one because it's it's on the inside. But the size of the Earth in regards to the size of the moon and this pi phi geometry. Now, a pyramid of Kepler is the 3:2 ratio. All these other pyramids have the same ratio, and that's a 3-4-5 triangle. Makes it up. And just so happens that was it John Neal or Michelle noticed this. This was not my. I didn't know. I'm just what they pointed out. 3-4-5 triangles fit perfectly in there. And again, not just the Kepler pyramid. Merenre and quite a few others that are mentioned within this series as well. The geometric connections that link multiple pyramids, also the angles of temples such as the Osirion, also in multiple places down in Thebes, so where Luxor and Karnak is, these major temples also have the same angles built into their alignments as well. But Earth and Moon embodied in there. And the moon is proportioned to the Earth it's 27.3% the size of the Earth. So 0.273 would be, now you're just moving it up. Now again, this is idealized at 7 to 11. If you look at the actual pyramid and the slight variations between the base, that 27.3 precise number that they even find on the NASA or Stanford or MIT is in there. You just got to include the imperfections. So we have this
7 to 11, the Great Pyramid angle, again in other pyramids as well, and also the relationship of these geometries which link the pyramids. But the pi and phi, but also the relative size of the moon to the Earth. Now at that 7 to 11 or the 14-11 triangle, it's 27.27272%. I'm just going to be rounding it off to 23 for a moment, because just like with pi and phi, and just as I showed earlier that the pyramid has slight variations in there, that 20 centimeter difference is too large for such an important building to have got that wrong. Just with a measuring cord, you would do a lot better. So even the stretching the cord ceremony, the foundation layings are so important, even in ritual sense. And it doesn't take just to stretch your measuring cord out, and get a 20% mistake, a 20 centimeter mistake. It's but this Earth and Moon relationship. So again, in this illustration, I have, defining it from the center, so the Earth and then the Moon. But you could also, again, as I showed earlier, express it this way, where the Earth is described by the square, and the circle goes through the radius. Now, why is that? Because now the Earth is a square, but now what happens if we define the Earth by the circle? Well, that's to do with the barycenter. So the Moon has mass, the Moon has weight, so it doesn't orbit the center of the Earth. It's pulling on the Earth as the Earth is pulling on the Moon. So where the Moon actually orbits is something called the barycenter, and that same 11 to 3 or 14 to 11 geometry just happens to define where the barycenter is. Now, Kepler's laws include, all orbits are elliptical. So that barycenter will move a little bit this way, and that essentially it's 27.3% below the surface of the Earth. That puts it at 1,000 miles below the surface of the Earth. It's going to move a little bit in between there because of apogee and perigee, but there's nice connections to consider that as well. So the Moon has a radius of 1,080 miles, and the barycenter will be at 1,080 miles, depending at which position between apogee and perigee. It will also pass through 1,005.3997 miles, which is 5,000 kilometers, the golden number times 1,000 kilometers. So this again, it's 7 to 11 can be found all over. Now, that they liked 7 to 11, this proportion, doesn't mean that they understood what the barycenter was. It doesn't mean they understood the size of the Earth and the Moon. The geometry on its own has a beauty to it. Just to understand one facet of something doesn't mean you understand every facet of it. So there is no written evidence for this, but these discoveries, such as the size of the Earth in regards to the Moon, does not require advanced technology. Through logic and some simple observation, Greeks and Romans were starting to understand this and had really good approximates of the size of the Earth. Also, relationship of distance between Earth, Moon, and Sun. So it's not out of the realm of possibility either. It's with very simple tools and observations you can achieve these things, astronomical geometric measures. This goes back before satellites. So it's the application of knowledge and logic, not the requirement of advanced technology to achieve this knowledge. So even though there's no smoking gun to say they understood about the barycenter and size of the Earth and the Moon, it is worth noting that Greeks and Romans went to Heliopolis to study from the Egyptians. So the geometry, the philosophy, and the Romans and Greeks there's no secret in that. It's not, they're quite open about the fact that they learnt from ancient societies to them, which was the Egyptians and the Chaldeans, or people, Babylonians as well. But at the very least, I always point to emphasize, even, that it is there doesn't mean they understood it, but it's not impossible that they understood it. And again, if the Greeks and Romans could do it with very simple technology, logic, and application of, basic knowledge and observation, then why not them? And also, given that the Romans, Greeks learnt from them, but point being, geometry and astronomy was sort of a quadrivium, and as we'll see more, these essential geometries also link Sun, Earth, Moon, but also planets as well, and that will be coming up. Kepler's law, which Kepler had 3 laws. I think it was law number 1, that all orbits are elliptical. The application of geometry is, where there is matter, there is geometry, as Kepler said, and Kepler's laws apply. So that's in the textbooks, that's acceptable. When it comes to the golden number, or phi, there's this air of mystery around it, and Devlin and Sortoy are sort of, these sort of, the high priests of maths, if you will. You can see that they have issues with the golden number. They don't like it, but it's there, and this architecture has been passed through time, still being used, and the applications of it to astronomy. So even, let's say they didn't know, they only sort of liked that 7 to 11 for aesthetic reasons, that is not the point. That does not really matter. What matters is that once you understand these basic geometries, you have now a system of learning to memorize. I had no idea about the Bary, where the Bary Center was, the size of the Earth, until I got interested in these mysteries, as they call them. I don't even like the word. Learning a handful of numbers, the golden number, the harmonic numbers such as 108, and looking at the connections between weights and measure systems, I understand, I can tell you where the planets are placed in the solar system, and the angles at which, well, it's available to me now because it's a way of memorizing and learning things, but also exploring things as well. So all of the mystery stuff aside, how did they, that's not really important to us in modern times. What's important is that these systems, such as the 7 liberal arts, especially the quadrivium, these essential elements in ancient architecture, they apply well to music and these other things, and to astronomy. So it's like, at the very least, you will learn so much about your natural world in a very simple way, instead of like a long string of random numbers with infinite decimals. These beautiful harmonic numbers will link one thing to another. Now, for instance, 27.3% is the size of the moon in regards to the Earth. The moon orbits the Earth in regards to a star every 27.3 days. The moon rotates on its axis once every 27.3 days. This also, like things like Charles's law or Avogadro's constant, where this 273 comes into it as well. It's just a beautiful system, and essentially, did they know in ancient times? That doesn't really matter. What matters is you can use this and learn things from it in a very simple way, but also, just like Kepler's laws and those geometries are in there, given how all these things will come together, like the sizes and distances, times, why is this so considered alternative or fringe or whatever? I don't understand it. But if only I had been taught this as a child. I come out of high school and went into when I first went into uni, I knew nothing about these things. I had no idea of it, and I had gone to I was interested in science. I was interested in astronomy. I had no idea. I couldn't tell you, the circumference, diameters, distances, ratios of size. But after getting involved in this, I can tell you all of it, not because I've memorized a million different facts, is just because I've focused in on these harmonics and these geometries that are built in there. And that's the wonderful thing about it. But Great Pyramid defining this circle and this square, which gives you essentially equal perimeter if you include the slight deviations in the side of each base of a pyramid, brings you even essentially to government work level of margins of error, like so small that it's essentially irrelevant in the real world. On paper, yes, but in the real world, doesn't matter. And, well, what more can you say? This is a redo of part 9 from the Understanding the Great Pyramid and Ancient Sciences playlist. Just include a little bit more clarification in there. Golden number, phi, Earth and Moon, Bary Center, all these things in there. Anyway, cheerio. And I'll fix the original playlist to put this this redo of number 9 in the proper position, and the link to the playlist will be in the description as well. And I'll close out with a small animation piece just to illustrate this. So if we start with a square defined by the base of a pyramid, and then we just tilt that up, and now we use the top of a pyramid to create this circle. Now we get that squaring the circle in the sense that the perimeter of a square is equal to the circumference of the circle. Very close to it based on 711 if you include the slight variations on each side. It's much closer. But also in regards to the relative size of the Earth and the Moon. Now we'll just drop in the Earth and drop in the Moon and how they fit within those particular geometries as well. And there you have it. Again, I've used the center point rather than enclose the Earth inside the square, but that's the same thing's happening. It's just a different viewpoint of that particular sets of geometry. Now, later parts of this series I go into it more and look at the same geometry defining distances between the planets as well, the inner planets, but also the relationship Saturn and Jupiter and their size and their orbital speed as well come into the same thing, especially if you consider the meter and the cubit and the 1 second pendulum, and well, the 1 second division, just like the 360 second division into minutes and seconds, dividing of time. This is a very ancient thing, and the use of a pendulum goes back. And in regards to 86,400 seconds per day, well, that's later in the series, but there you go. Same. So if I take them again, pyramid is a three-dimensional object. You can see it's not a triangle, and if I look at it in that sense, I see the maximum visible base, including the sockets at the corners. Multiply that by the number of seconds per day, I get the equatorial circumference of the Earth. Now, with that same essential geometry, I take the height of a pyramid and I multiply that by 86,400 seconds per day. I get the polar diameter of the Earth. So you're describing an oblate spheroid within there. So again, it's so many harmonious coincidences between weights and measure systems, geometry, and astronomy. Now, you can be a so-called conspiracy theorist, but you can also be a coincidence theory theorist as well. And they're not so different from each other, though one has less social stigma, to put it that way. But yeah, there's so much to this. This is part of a really, really long series. I go through all different aspects of that. If you just view one particular piece and what I'm saying in there, well, yeah, you can sort of wave it off. But if you look at the whole piece, and it takes hours and hours and hours just to get introduced to it. And then the question is, how do these things all work together? How did this all fall in place so beautifully, so perfectly? How is it that these same geometries and weights and measure systems have been passed through time, through various architectural traditions, also dropped into various mythology as well, and still define the modern world today? Why not a decimal clock? Okay, but with that, hope you enjoyed and have a good one.